All right, let's go ahead and get started. I want to welcome you to Unit 12. This is Acids and Bases, and I especially want to welcome our new subscribers from El Cajon, California, Granite Hills High School. Welcome on board. Good to have you. Also, homeschool student from, and I'm not sure if I'm pronouncing this right, Jeremy from Nanaimo, British Columbia. Jeremy, I understand that your mom is an ex-chemistry teacher, so that should be very helpful. And so good to have you all, and let's get started. So here we go, Unit 12, acids and bases. So let's start with the question of where acids and bases are. And the answer is they're everywhere. They're all around us. In fact, as we're going to see in just a moment, they're in us, right? We don't have to go outside of our bodies to find acids and bases. They're in our bodies. So some common acids include things like vinegar, stomach juice or stomach acid, coffee, citrus juice, and sodas. So as you can see, they're everywhere. Most foods are acidic. Most foods are acids, and most cleaning solutions, by the way, are basic. So common bases include things like baking soda, lye, bleach. Most cleaning products, all those are basic. And by the way, an important problem that we're having environmentally is the issue of acid rain. And acid rain is formed primarily through the burning of fossil fuels. So that's an issue that is going to have to be dealt with in the very, very near future. So as you can see, acids and bases is an important topic for us even outside the chemistry laboratory. We don't have to just think of ourselves as chemistry students to have to think about acids and bases. These are issues that affect us environmentally, and it's important that we have some kind of an understanding of acids and bases. So let's go ahead and deepen our understanding. First of all, let's talk about some characteristics of acids. Well, first of all, acids increase the hydrogen ion concentration in a solution. That's by definition. They increase the hydrogen ion concentration in a solution. So that's the first thing. The next thing that they're going to do is they're going to make a pH that's less than 7. We're going to talk a lot more about the pH scale in just a moment, but for now we'll just say this. The pH is less than 7 for an acid, less than 7. They turn blue litmus paper red. Now, litmus paper is what we call an indicator. I'll show you this in the laboratory, and it tells us whether something's acid or base. But if it's blue litmus paper to begin with, it turns red, you're dealing with an acid, okay? Next, they react with active metals to form hydrogen gas. So if you, for example, have zinc and you mix it, you put the zinc metal into acid, hydrochloric acid, for example, it's going to produce hydrogen gas. It's an electrolyte. In other words, it's going to dissociate in water and it's going to produce an electric current. And it tastes sour. So if you've ever eaten a lemon, and I'm sure you've not eaten a lemon, but tasted a lemon. I don't know why anybody would eat a lemon. But if you've tasted a lemon or a lime or any citrus type fruit, you know that it tastes sour. Well, that sour taste is an indication that you're dealing with an acid. All right, so that's an acid. What about base? Well, bases increase the hydroxide ion concentration in solution. By definition, that's the definition of a base. They increase the hydroxide ion concentration. They have pHs greater than 7. They're going to have a pH higher than 7. They turn red litmus paper blue, right? They turn red litmus paper blue. Now you're probably asking, well, what do they do to blue litmus paper? Nothing. It just stays blue. So red litmus paper is going to turn blue if you've got a base, okay? They, like acids, are electrolytes. They dissociate and they conduct electric current. That's what electrolyte means. They taste bitter. I wouldn't recommend it, but if you were to taste a little bit of baking soda, it would have a bitter taste, right? Don't do it, but just take my word for it, okay? And finally, it turns a chemical called phenolphthalein pink, okay? It turns phenolphthalein pink. If it's an acid, the phenolphthalein will remain clear, but if it's a base, it's going to turn it pink. So that's that. Now, the pH scale is a measurement of how acidic or basic something is. So the pH of 0 is the most acidic. So down here, this is acidic. And the pH of 14 is the most alkaline or basic. Now, alkaline is another name for basic. It's the same thing, okay? And so what's right in the middle? Neutral. So a neutral pH is a pH of 7. So once again, low pH, like 0, for example, is acidic. High pH, like 14, basic. Right in the middle, you're talking about a neutral pH. Okay, 7 is neutral. All right, let's talk a little bit about some definitions of acids and bases. The first one was proposed in 1884 and is called the Bronsted-Lowry definition. The Bronsted-Lowry definition of acids says this, that acids donate protons. That's how you know that you've got an acid. They donate protons to the solution. And a Bronsted-Lowry base, by contrast, is a proton acceptor. So let's look at this reaction here. This is what's called an equilibrium. We'll talk a lot more about equilibrium later. It's when the arrow goes both ways. We won't worry about that right now, that aspect of it right now. If we take water, which is obviously liquid, and we take ammonia gas, and we put them together, we get ammonium ion, that's NH4 plus, aqueous, plus OH minus, aqueous. But I want you to notice, if you go left to right, and that's the direction I want you to look right now, left to right, what's happening to the water? Well, water gave up a proton to the ammonia. How do you know? How do you know that water gave up a proton to the ammonia? Well, look at it on the other side. It's not H2O over here. It's OH minus. That's one hydrogen less than it was on the left-hand side, isn't it? So that means water gave up a proton. And what does the Bronsted-Lowry definition say about Bronsted-Lowry acids? They're proton donors. They're proton donors. Well, if water gave up a proton, then ammonia accepted it. So proton acceptors are bases. So in this case, in this equilibrium, the acid is the water and the base is the ammonia. Now you might be thinking, wait a minute, I thought water was neutral. I thought water was neither an acid nor a base. Well, as it turns out, water is something called amphoteric. That means it can be acid or it can be base. And now you know, okay? All right, let's look at this little diagram here. It says Bronsted-Lowry acids and bases. So again, the water in this case is giving up a proton. How do I know? Because on the other side, it's lacking a hydrogen. In contrast, the HCO3 minus gained a proton. How do you know? Because over here it's got the proton that it didn't have over here. So it must have gained the electron. So the acid is the water and the base is the HCO3 minus. Now, if I look at it in the opposite direction, I realize that's a kind of a foreign concept to you at this point because we haven't talked about equilibrium, but just for moments, for this time, let's think about going in the opposite direction. We'll talk about equilibrium later. The acid would be the H2CO3 because it gives up, if we look this way, it gives up a proton, right? It's no longer H2CO3, it's HCO3 minus now. So it gives up a proton. We call it an acid, but because it's on the right-hand side, we call it the conjugate acid. Conjugate acid. And likewise, it gave it up to who? OH minus, because it's H2O over here, or HOH. So it is the conjugate base going the other way. All right? So we've got acids, we've got bases, we've got conjugate acids, and we've got conjugate bases. So when the reaction is looked at in reverse, the acids and bases are called conjugate acid and conjugate base. Okay? Conjugate acid and conjugate base. So notice that the acid is still a proton donor, and the base, whether it be a normal base or a conjugate base, is still the proton acceptor. All right, so that's Bronsted-Lowry. Now let's look at a different way of looking at acids and bases. So another important way of defining acids and bases is called the Arrhenius definition. The Arrhenius definition. And this definition holds that acids in solution increase the hydrogen ion or the hydronium ion concentration. And I'll talk about hydronium ions in just a moment and their relationship to hydrogen ions. For right now, we know that by definition, Arrhenius acids increase the hydrogen ion concentration, while bases increase the hydroxide ion concentration. The hydroxide ion concentration. Thus, the greater the hydrogen ion concentration, the lower the pH, right? The lower the pH. So let's look at three relationships, in fact, every possible relationship between hydrogen ions and hydroxide ions. So let's start with what happens if the hydrogen ion concentration in a solution is the same as the hydroxide ion concentration, if they're equal. What does that mean? Well, that means the solution is neutral. The hydrogen ions and hydroxide ions are exactly balanced, so the pH is neutral. It is 7. So that's the first scenario that we'll look at. But what if the what if the hydrogen ion concentration is greater than the hydroxide ion concentration? If that happens, we're going to say that the pH is lower than 7. Okay, the pH is lower than 7 because of the fact that there's more hydrogen ions than there are hydroxide ions, and the hydrogen and the solution is acidic. Okay, the solution is acidic. And finally, what happens when the hydrogen ion concentration is less than the hydroxide ion concentration? Well, in that case, the solution is basic and the pH is greater than 7. So there you go. That's all three scenarios. Hydrogen ion and hydroxide ion concentration are the same. Hydrogen ion concentration greater than hydroxide ion concentration. And finally, hydrogen ion concentration less than hydroxide ion concentration. And they are neutral, acidic, and basic in those situations. Okay? All right, let's move on. Why is hydrogen ion concentration and hydronium ion concentration the same? Why? Okay, here's why. Because the moment the hydrogen ion becomes present, because we said that an acid donates protons, but to what? It donates protons to a solution that has water in it, right? Water's everywhere. Water's always present. So when you drop that hydronium ion concentration into the water, the moment it gets into the water grabs it, and it becomes a hydronium ion. So there's no such thing as free hydrogen ions for the most part. There's no such thing as free hydrogen ions running around. They're all hydronium ions, right? So when somebody says, what's the hydrogen ion concentration? They really mean the hydronium ion concentration. So we can safely say that the hydrogen ion concentration and the hydronium ion concentration are the same. They're equal. Okay? Does that make sense? So let's look at another example. Let's go back to the Bronsted-Lowry definition of acids and bases and look at another example, this time from a Lewis diagram standpoint. In the diagram below, notice that the acid is the proton donor and the base is the proton acceptor. So here we've got water, right? And water has a proton to donate, and it's going to donate it right there. There's a lone pair of electrons on the ammonia, and that lone pair of electrons is going to attract that hydrogen and pull it to itself. In doing so, the water is going to lose the hydrogen. So what do we call things that lose hydrogens? Acids. What do we call things that gain protons? Bases, right? Now let's go the other way. Let's go right to left. On this side, the ammonium ion has a proton to donate. So we're going to call that the conjugate acid. And the base is the one that accepts the proton. We're going to call that the conjugate base then. Okay? The conjugate base. So water loses the proton, so it's the donor, while ammonia gains the proton, or the water is the acid, it's the donor, and the ammonia gains it, so it's the base. Right? It is the base. All right. How are the hydrogen ion concentration and pH related then? How are they related? Folks, I think that this is a good place for us to stop and just go ahead and get ready for our next lesson, which is going to be this relationship between pH and the hydrogen ion concentration. I'll just tell you briefly that the pH is minus the logarithm of the hydrogen ion concentration. If you have time between now and the next unit, or the next lesson, I should say, in this unit, take a look at what your math teacher had to say about logarithms. What is a logarithm, right? Because we're going to need to know that for our next one. Folks, I'll see you on the next. Thanks.